Hello students. In this session I am going to explain about the digital to analog conversions. Digital means what that one? Numbers. The numbers are displayed on that one. You can see that one, that is a digital. For example, it is a digital clock and the analog clock. Digital clock are 9:15, it mentions it is a digital. Yes, analog clock is 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This shows the this shows the uh, analog analog clock, and this one is a digital clock. Right, this is the difference between the analog and the digital. In your lab also you have a voltmeters. Yes, DMM is a digital multimeter. Your normal voltmeter is a analog voltmeter. That is the reason for that one. It is a analog and the digital. Right, digital and the analog signals are continuous of the values over the given range, constructed in the discrete values. Right, the quantity has a continuous of the values given the range is known as a analog quantity. A quantity that has only two discrete values, high or low, it is called it as a digital signals. For example, op amp is an analog, IC 555 is a digital. Like the systems of perform the internal operations of the binary or some type of the binary codes can be given for that one. Right, if you are giving the analog to digital conversions, the process of conversion from the analog signal to the digital signal is referred to as a ADC, otherwise uh, analog to digital conversions, ADC can be call it. It converts the ADC. Measurements of the process parameters are analog. Natures are usually transduced and sent. An analog to digital converter can we call it as a ADC. Can we call it as a ADC? ADC means analog digital converter. Yes, that is a analog digital converters can be call it as that. Next, converts the digital input signal into the analog output signals. The digital signals are represented with the binary codes, which is a combination of the bits 0 and 1. The chapter deals with the digital to the analog converters. How to convert this one? Yes, digital to analog converter DAC consists of a number of binary inputs and signal output. General number of binary inputs of a DAC will be power of 2. There are the two types of DACs, weighted register DAC and the R to 2R ladder DAC. And before that one, we are converting from that analog to digital converters. Can we see that one? Can we see that one? In the, for example, can we take in the analog to digital to analog converter, can be write it as a ADC to the analog to digital converter and the digital to analog converter. Yes, DAC, the converter which converts the binary weighted numbers. The either an electric voltage or an electric current are called as a digital to analog converter. The definition of the digital to analog converter, it converts which converts the binary weighted number of the to the either an electric voltage or an electric current are called as a digital to analog converter. Right, it is a digital input, it is the digital to the analog converter and the analog output. This is the way of the convert to digital to analog. There are the two types of are there one. First one is a weighted register, and the second one is a R to 2R registers. I'm going to explain about the analog to digital converters. I'm going to draw that one block diagram of that DAC. Is it is a DAC. It is the n number of input, n 2 raised to n number of the input given that one. We are getting the V out. It is in the analog. Yes, this is the analog for that one. Input of the DAC is a n-bit binary signals available in the parallel forms, and are signals available at the output of the latches or the registers, and the voltages corresponding to the digital 0 and 1 logic are available to drive the converter circuit, are not precisely fixed voltages. This is not a fixed voltage, it is there one directly to the convert from the used in the operator. Digitally controlled switches, digitally controlled switches are there for this one. Yes, switches are there. In the block diagram of this 4-bit D to A, it is there. If for example it is a 4-bit converter, can be write it like that one, can be write it like that one, can be write it in the 1 2 3 4 4 bits are there. Yes, one output it is there, one output it is there. This is the D to A converter. A B C D, it is the number. I am going to give that one. A B C D, four numbers are there. I am going to see that one. This is the truth table I am going to write. Yes, these are the binary signals. This is the analog signals. It is a 0 0 0. It is a 0 0 0 0 1 is a 1 0 0 1 0 is a 2 till you have to 15, till you have to write the 15. 1 1 1 1 can be write it, can be write it like that one. It is the list of the binary to the analog conversions. It is a binary to the analog conversions. I am going to take that one. I am going to take that one. It is in that one. It is a DCBA. It is the analog signal. It is the 2 raised to 0 is 1. That is the binary number 0001. 2 raised to 0 is 1. 2 raised to 1 is 2. 0010. 2 raised to 2 is 4. 0100. 2 raised to 3 is 8. 1000 can be write it like that one. That's why we can call it as a 1248 numbers. 1248 numbers can be got to know that one. This is the conversion of the binary signal into the analog signals. This is called it as a binary signal into the analog signals. Yes, this is a converter. That's why the LSB is called it as the least significant bit is 2 raised to 0 is 1. MSB is called it as a 2 raised to 3 equals to 8. Example, I am going to take the inputs A, B, C, D. I am going to take the example A, B, C, D. Yes, A, B, C, D, I am usually take that one in the registered digital system. 2 raised to 4 is a 16. It is separated this one. I am going to take that one. 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3 can be write it like that one. Yes, for example, in the LSB A is a 1 volt, B is a 2 volt, C is a 3 volt, D is a 4 volt. Sorry, B is a 2 volt, C is a 8 volt, sorry, 4 volt, D is a 8 volt. Yes, our binary number is our binary number is 1 1 1. I'm going to calculate the voltage of this one. 1 volt into 1, 2 raised to 3, plus 1 into here. Sorry, here. 1 into 2 raised to 2, plus 0 into 2 raised to 1. I'm going to write that one. That is the final number is 1101. Yes, 1 volt is A equals to 1, B equals to 2, C equals to 4, D equals to 8. Correct? Uh, Comes from here to here. A, B, C, D. Yes, this is the equation for that one. 1 into 2 raised to 3 plus 1 into 2 raised to 2 plus 0 into 2 raised to 1 and 1 into 2 raised to 0. Yes, this is a 8 plus 4 plus 0 plus 1. 12, 13 is a 13 volt will come like that one. This is the conversion of that one from the binary system into the analog. Binary system into the analog conversions. This is the binary systems into the analog conversions. Now I am going to explain about this one of the weighted registers, and the accuracy and the resolution of the weighted registers can we see that one. Before going to explain about the DAC of the accuracy. DAC of accuracy. The accuracy indicates how close the measured value is to the true value. And accuracy of the 1% means, the accuracy of the 1% means it is a 100 volts. Accuracy of the one means that 100 volts might really be the 99 volts to 101 volts, the between that one. Yes, DAC is manufactured have a many ways of specially accuracy. The most common called as a full scale error and literality error. They are normally expressed as a percentage of the converter scale output. In the percentage full scale of that one can be written. Full scale error can be DSP output that one. Literally can be written in the low as a low of that one 0.001%. Yes, in general purpose DAC accuracy of the 0.012 to 0.1 percentage range of the accuracy it is there one. Offset voltage can be take that one. Offset voltage of the output of a DAC will be 0 volts when the binary input is all are 0. Yes, the output is the output of DAC equals to 0 volts. The binary input is also a 0. Yes, there will be a very small output voltage situation called offset error. And next one is a resolution. Resolution means what? Resolution is a defined in the resolution means the resolution means it is a D to A converter defined as the smallest change can be occur in the analog input results of the change in the digital inputs. Percentage of the resolution can be written step size divided by full scale. into 100. Yes, although the resolution of the expressed in the amount of the current per steps can be used for that one. That is the resolution of percentage of the can be calculated from that one. Yes, the percentage of the resolution can be used. For example, uh, in the before the sessions we have seen the resolution is 1 volt. For example, resolution is 1 volt. The scene V naught is changes is not less than the 1 volt. In the code changes, the resolution is always equal to the weight of the LSB. The resolution is always equals to the weight of the LSB. Weight of LSB, least significant number, whatever that one, it is always equals to. And then the step size can be, what is the step size? Step size is that one being the continuously cycled 16 states by the clock inputs. Waveform of the D to A is respective of in case 1 volt is a step counter is 0000 to 11111 counter. D to A output turns to 0, counter turns to 000. 0 to 1 is a step is high. Like that can be write it like that one. That is a full scale output. Yes, that is the percentage of the regulations can be seen that one. First one is a weighted resistors. Weighted resistors are there in the weighted resistors in the D to A converter. We can use that one. This is the circuit diagram of the weighted resistor. This is the circuit diagram of the weighted resistor. This is the LSB and this is the MSB. This is the op amp. It is a negative feedback for that one. I am going to take that one negative input, it is there. I am going to take that one in the 3-bit number. In the 3-bit number, I am going to take that one. Is that number 100 can we take that one? Can we write it? This one is a negative, is a 2R with the feedback RF into minus VR. It is a ground. Yes, that is equals to output of the op amp is minus RF divided by RI into Vin. Instead of this one, I am going to take that one. Minus RF divided by 2R, it is there. Minus VR can be take it divided by RF. This one is get cancels. VR divided by 2 is the 3-bit data. It is in the 4-bit, 1 by 4 will come for that one. This is the way of the calculate the 2R, it is there. 2 raised to 1, 2 raised to 2, 2 raised to 3, like that one. 2R, it is there. 2 raised to 1, it is there. Yes, that is the way to identify the numbers. The main problem of converting the digital signal into the equivalent signal is change the n digital values. This is the n number of the LSB, it is there. Right, that is the, can we see that one? Yes, VR by 2, how it comes from the op amp. Yes, next. One of the simplest circuits shown in the figure. You have seen that one. Use the summing amplifier with the binary weighted resistors. Work as a n electronic switches D1, D2 and the Dn. Controlled by the binary input word. These switches are single pole double throw. Yes, type. If the binary input to a particular switch is 1, that connects the resistance to the reference voltage minus VR. Here it is there, minus VR. Connections. Non-inverting terminal connects to ground minus VR, and if the inputs are zero, switching connected to the register ground from the that figure, the output current I naught is the ideal op amp. The comparing the equations 1 and 2 can be Rf equals to R, K equals to 1, VFS, voltage full scale equals to VR. Then the circuit, you have seen that one. The negative reference voltage, why it is a negative reference voltage? It is a non-inverting terminal connects to ground, that one negative feedback it is there on that one. Yes, that is the 3-bit weighted register DAC implied noted that the output of an op amp in the figure, it is connected in the non-inverting mode. The op amp is simply working in the current voltage converter. How it comes like that one I have explained. Yes, VR divided by R. Yes, V naught equals to I naught into RF. The polarity of the reference voltage is chosen according to with the type of the switch. For example, TTL, transistor logic gate. Yes, the reference voltage should be 5 volt and the output will be negative. The accuracy stability of the DAC depends upon the accuracy of the resistance. Tracking each with the temperature, there are however the number of problems associated with the DAC. Here they can give that one. Reference voltage will be the 5 volt. Imagination. The output will be negative. Why the negative? It has a negative feedback. Accuracy and the stability of the DAC depends on the accuracy of the resistors and the tracking of each other. Its temperature. There are, however, the number of problems associated with this type of DAC. One of the advantages of the binary weighted type of the DAC is the wide range of registers values required. It may be observed that for the better resolution, the input binary word length has been increased. The number of bit increases, the range of resistance value increases. For 8-bit DAC, the register required are 2R, 2 1R, 2 2R. 2R equals to means that one RF equals to 2 RF is a note that one. Like a Wayne bridge oscillator, you have seen that one. DAC. 12-bit DAC is the largest resistance required in this one. In the 5.212 mega ohms registers can be used that one. This is the working condition of the DAC. This is the most significant bit. This one is the least significant bit. Can be used for that one. For example, 100. It is the least significant bit. This is the most significant bit. Can be take it like that one. That is the circuit. You have seen that one. Yes, it is the only a 3 bits are there. We can see that one. Otherwise the 4-bit will come. 4-bit will come. That time what will come for that one? VR divided by 2 plus VR divided by 4. It is a 4-bit. 2-bit is a VR by 2. 4-bit is a VR by 4. Can be used it in the 4-bit. 3 VR divided by 4. Can be write the 4-bit value can be write it in the weighted registers. It is the weighted means the weight of the registers can be used for that one. It is the depends on that one. Yes, that is the weighted registers values. Yes, going to draw it separately like that. This resistance can be write it in that one. It is the registers R naught by A R naught by 4, R naught by 2. Like that one can be used like that in the circuit of the using the weighted registers. We know that one binary coded decimal codes uses in the 4-bit characters. 4-bit characters, right? For the decimal number, it is a representation of that one 0 to 9 number systems are there. Least significant of the LSB of that one represent the 0 into 2 raised to 0, it is a LSB. Yes, the next bit is a 1 into 1 or 0 into 1 or 0 into 2 raised to 1, 2 raised to 2, 2 raised to 3, it is a 8-bit data can be taken. Notice that 10002 and 111 there are the 15 discrete elements are there. Yes, can be used 2 raised to n position will be the cause 15 into 1 by 15 equals to 1 volt can be taken. 2 raised to 1 is a 2, 2 raised to 0 is a 1 can be clearly seen in this representation of that one. Yes, this is the weighted registers of the binary numbers. The resistive divider must be following the things of the order. Change the digital input into the equivalent analog output is the 2 raised to 0 bit. 2 raised to 0 bit must be changed to 1 volt, and 2 raised to 1 bit can be changed into the 2 volt. 2 raised to 2 is a 4 volt, 2 raised to 8 is a 3 is a 8 volt. These four voltages represents the digital output and summed together to form the analog output voltage. Resistive divider, it is the can be written in that one R0, R1, R2, R3, Rn can be written like that one. Assume that the digital signal 0001 applied to the network. We know that one 0 equals to 0 volt, 1 equals to 15 volt. Yes, equivalent circuit is in this circuit can be seen that one VA will be calculated in the output voltage. Yes, can be write it like that one. Yes, it is in the zero. It is a 0 volt, and it is a 1 volt. It is a 15 volt. Can be take it, and can be write it like that. V naught divided by R naught plus V1 divided by R naught by 2, and V2 divided by R naught by 4 can be write it V3 divided by R naught by 8 can be write it. 8 can be write it like that one divided by 1 by R naught plus 1 by R naught by 2 can be simplify this 1 divided by R naught by 4, 1 divided by R naught by 8. We are simplifying this. After simplifying this equation can be write it it is 15 by R naught divided by that is also 15 R naught can be get it, and the 1 volt can be get it like that one. This equivalent circuit can be 15 output combination can be write it in the minimum theorems can be used. This is the circuit, can be draw it like that one. This is the resistance. RL is greater than equals to R naught. R naught, R naught by 2, R naught by 4, R naught by 8. This is the way to write that one. Yes, this is the way to write this circuits. This is the, before that one I have read that one. R naught by 8, R naught by 4 can be write it in the resistive ladder network for that one. The summarize the resistivity divide in the building the change of the digital voltage into the equivalent analog voltage. There must be some one input register for the each digital bit. In this digital bit, in this digital bit can be write it, this is the only one digital bit. Yes, and the beginning of the with the LSB, each of the following registers of the half size of the previous registers. LSB it is a LSB is beginning each of the following registers one and half of the size of the previous register. Previous register. Okay, the full scale output voltage equal to the positional voltage of the digital output. LSB has a weighted of that one. The weighted weight of LSB is 1 divided by 2 raised to n minus 1. That is when the n number of inputs. Yes, this is the way to the weighted registers of that one. The fabrication of the such largest resistance IC is not a practical also. Voltage drop across the large resistor to bias the current would be also affected the accuracy. Choice the smallest register value 2.5 kilo ohm reasonable. Otherwise, the loading effect of the terms is difficulty of the achieving the maintaining the accurate over there. Yes, in the next it is, this is the, what is that one, step size. Step size it is a, this is the way of the VR. I have explained before that one. 1 by 2R. Yes, 2 by 4R. Like that you can see that one. The resolution of D to A converter defined in the smallest change can be occur in the digital output. For example, I am going to take that one. It is a 4-bit counter. 4-bit counter. You are giving the, in this here it is a 1000 counter like that one. This is the clocking. It will goes like that in the numbers. It is a 000 counter can be given the input. That will go there one. It is like that you have to use that one. Can we see that one? The 000, the DAC output returns to the 0 volt. The resolution steps of jumps in the staircase waveform. In this case, each step is a 1 volt. This is the 1 volt. Note that staircase has a 16 levels. 16 levels it is. Why it is 16 levels? It is a 0 to 15 number of voltages, binary values are there. Note that in the staircase 16 levels corresponding to the 16 input states. Yes, and the full scale in general for an n bit DAC, the number of different levels will be the 2n. The number of steps of 2n minus 1 may already figure out the resolution steps into that one. The analog output k into digital input, a new interpretation expression of the would be the digital input is equal to the number of the steps k is the amount of voltage per steps, and the analog output is the produces the two outputs. Yes, this is the way that one percentage resolution equals to, although the resolution can be expressed as the amount of voltage current steps, also useful in express the percentage of that one. In that figure we have explained the full scale of the output is 15 volt, digital voltage of the 11111, the step size is 1 volt, the percentage 1 volt divided by 15 into 100 is 6.67 is a resolution of the weighted resistors in that one, and means that one 16 steps are there, 15 is a decimal number with a one input, step size is a 1 volt. They have told that every step says ಒಂದೊಂದು ಸ್ಟೆಪ್ಪಿಗೂ ಅವ್ರು ಎಷ್ಟು ಡಿಫ್ರೆನ್ಸ್ ಇದೆ ಅಂತ ಹೇಳಿದ ಸ್ಟೆಪ್ ಸೈಜ್ ಅದು 1 ವೋಲ್ಟ್ ಅದ. ಅದ್ರದ್ದು ಟೋಟಲ್ ಎಷ್ಟು ಹೈಯೆಸ್ಟ್ ನಂಬರ್ ಸೈಜ್ ಅದ 1 divided by 15. 1 divided by 15 means 0.667 can be used into the 100. 6.67, this is a 0.06 into 100, 6.67%. It is a resolution of the weighted register. Okay, so please watch our videos regularly.